Namaskar students. Today in this video we will discuss about equations which can be reduced to exact differential equations. If you remember our last lecture, in last lecture we have discussed about exact differential equations, the condition of exactness and the solution of exact differential equations. Here today we will be talking about differential equations which are not exact, but with the help of integrating factor, they can be reduced to exact differential equations. Now, what are integrating factors? Integrating factors, these are the functions of x and y. They may be function of x only, they may be the function of y only, or they may be function of both x and y. When we multiply the equation with these integrating factors, the equation becomes exact. And once it becomes exact, then we can easily solve it by the way we solve exact differential equations. Now, if any equation has integrating factor, then that integrating factor is not a unique. We can find out infinite integrating factors for that differential equations. Now the question is how to find out this function of x and y for making equation exact. So we have some rules depending on the form of differential equation to find the integrating factor. So first of all, we will be discussing these rules and then we will be taking problems where we will be reducing equations to exact form and then we will be solving them. So let us start with the first one. The first one is if differential equation mdx plus ndy is homogeneous and it is not exact because we are discussing here the differential equations which are not exact. We have this equation which is not exact and which is homogeneous. So in such cases, this is homogeneous differential equation. In such cases, the integrating factor, this I stands for the integrating factor. This is given by 1 by mx plus ny. We have m here, we have n here. From m and n, we will be evaluating this integrating vector. Multiply this differential equation with this integrating factor. The equation will become exact and then we can easily solve it. Now the second rule for finding the integrating factor is if we are not able to apply this first rule because if m and n they are not the homogeneous functions, then we can check for the second rule. What is the second rule? If the differential equation has the form y some function f1 of xy dx plus x some function f2 of xy dy equal to 0. If we have a differential equation of this form, here f1 and f2 are two functions of xy. If we have this form, then we can find out integrating factor as 1 divided by mx minus ny. Be very careful, here we have plus in the first rule and here we have minus sign. Now suppose we have a differential equation which doesn't satisfy these two things, neither it is homogeneous and neither it is of this form, then how we can find out the integrating factor. So we are moving to the next rule. Third one. The third rule is, suppose we have a differential equation mdx plus n dy equal to 0, and it is not exact. We have two cases here. The first case is, we will be evaluating partial derivatives. Find del m by del y, partial derivative of m with respect to y, and minus partial derivative of n with respect to x, and is divided by n. If we are getting this as function of only one variable, say f, and that one variable is x, then in this case, if we have this thing that we are getting it as a function of x only, then we can write here it is function of x only. Then the integrating factor in this first case is given by e integration of this function f with respect to x. So this will be integrating factor. We will be multiplying equation with integrating factor on both sides, and after doing this, the equation will be exact. The second case is here. Here we consider this difference, partial derivative of n with respect to x, then partial derivative of m with respect to y. We have to divide this difference with m, this function m. It is a function of both variables x and y. If we are getting this as function of only one variable, and now that variable is y, g is the function here. It is a function, gy is function of y only. If we are getting it like this, then we can proceed further for finding the integrating factor. Here the integrating factor will be e raised to power integration of this function g with respect to y. Now, if you see it carefully, then there's a difference in the numerator in both of these cases. Partial derivatives which are involved, they are same, but here we are considering partial derivative of m with respect to y minus partial derivative of n with respect to x, and here we are considering it in the reverse order. So if first and second rule are not applicable, then we can go with this third one, and if this is also not applicable, if we are not getting here function of one variable x, and here we are not getting the function of one variable y, then this is also not applicable. Then we can go for the fourth one. What is that fourth rule? If we have the differential equation of the form x raised to power a, y raised to power b, m y dx n x dy plus x raised to power c y raised to power d p y dx plus q x dy equal to 0. Here all these a, b, c, d, m, n, p, q are some constants. If you will see this equation carefully, you can see here we have 4 terms here in this differential equation. We have 2 terms with dx and 2 terms with dy. So if we have this type of differential equation, then here we assume that integrating factor is of form x raised to power h, y raised to power k. Now what are these h and k? These h and k are chosen in such a manner that when we multiply this equation with this integrating factor x raised to power h, y raised to power k, this differential equation becomes exact. So this is the 4th rule. The last way for finding the integrating factor, or we can say for reducing equation to exact equation, is inspection. As the name suggests, inspection, it means here we have to do some little work, we have to do some analysis to find integrating factors. There are some differentials which helps us in finding integrating factors. We know, suppose we have in any differential equation, we have the terms like x dy plus y dx. How we can write this? We can write this that it is equal to d of x, y. Similarly, we have some other differentials which can help us in doing analysis to find the integrating factors. So we have these 5 ways for reducing the equations to exact form. Now, let us consider some problems. The first one is we are not solving them. We will be just identifying that what is the form of that differential equation, and depending on that form, we will be deciding here that which rule will be used for finding the integrating factor. So let us consider the equations. The equations are x square y square plus xy plus 1 y dx plus x square y square minus xy plus 1 x dy equal to 0. Now, it is of the form m dx plus n dy equal to 0, but when you will check the condition of exactness, it will not be satisfied. means this given differential equation is not exact. Now, the question is it possible to reduce it to exact form? For that, we have to check that out of those 5 rules which we have discussed right now, which is applicable to this differential equation. Now see here, this is m. If you will see this one, this is function of xy. This is some function of xy. Then we have here y. f1xy y dx. Now similarly, if you check this one, x square y square minus xy plus 1, this is again the function of xy. Let us name this as f2. Then we have this x dy equal to 0. Now, if we see the results, rules which we have discussed, then this is the second case. Y f1xy dx, x f2xy dy equal to 0. Integrating factor will be 1 upon mx minus ny. So this is of second type. So we will be finding the integrating factor. Integrating factor will be 1 upon mx minus ny. After finding this integrating factor, multiply the equation with this integrating factor. The equation will become exact and then solve it further. Consider second example. The equation, differential equation is y plus y cube by 3 plus x square by 2 dx. This is m dx. 1 upon 4 x plus x y square, and this one only dy equal to 0. Now, when you will check the condition of exactness, again it will not be satisfied here. Now let us see that which rule will be used here for finding the integrating factor. Now this is not a homogeneous function, so the first is not applicable here. If we talk about the second one, then this can't be written in this form, some function of xy by dx. So the second rule is also not applicable here. If I talk about fourth one, in fourth one, if we see that this one, here we have how many terms? We have 4 terms. But if we see this one, then I have 5 terms. So that is also not applicable here. So we will be trying for the third rule. For third rule, we need the partial derivatives. So first of all, what is m here? M is y cube by 3 x square by 2 and n is this. I am not solving here these problems. We are just discussing here that which rule will be used. Now let us evaluate the partial derivatives which are used in rule 3. Those partial derivatives are del m by del y. Del m by del y will be 1 and it will be y square. And del n by del x will be 1 by 4, 1 plus y square. Now see, we have the partial derivatives with us. Now, for which case we should try? Here, if we see the difference, we will get 1 plus y square in the difference with some constant. If we will be dividing it with this m, then it will not be reduced to function of one variable. But if we will divide this difference by this n, it will reduce to function of one variable, and that one variable will be x, because 1 plus y square will cancel out. So we have to divide it by n. So it means out of these two, this one will be used. So coming to the problem, consider del m by del y minus del n by del x whole divided by n. We are considering this one, so we can write here, consider this one. The difference will be, this is del m by del y, this is del n by del x. The difference will be 3 by 4, 1 plus y square divided by n. N is 1 by 4 x 1 plus y square. What we will get? We will get 3 by 6. Now, this 3 by 6 is function of only one variable, and that variable is x. Now, this is not the integrating factor. After this is our function fx. So the integrating factor will be e raised to power this 3 by x dx, which will be e 3 log x, which will be x cube. So for this second example, we have used third rule for finding the integrating factor. Now multiply the equation with this integrating factor, it will become exact, and then solve it. Now let us consider one more problem. The problem is, solve the differential equation 3x y square minus y cube dx minus 2x square y minus x y square dy equal to 0. Again, you can check that this will not be an exact differential equation. Now let us see which rule will be easily applicable on this differential equation. In some problems, we may apply more than one rule for finding the integrating factor. Here, this is m and this is n. This minus sign will be in n because the general form is m dx plus n dy. Its degree is 3, the degree of m is 3, and the degree of this n is also 3. So this is a homogeneous equation, So the first rule is applicable here. So we will be using the first rule. We will be finding the integrating factor by using this result, 1 upon mx plus ny. So simplify it, you will get the integrating factor, multiply equation on both sides with this integrating factor, equation will become exact, and solve it. Now let us consider one more problem. Fourth one. The problem is solve the differential equation x y square plus 2x square y cube dx plus x square y minus x cube y square dy equal to 0. Now how we can reduce it to exact equation? This is our m. This is not a homogeneous one. So first one is not applicable. Is it possible to write it in second form according to second rule? For second rule, we need here some function of x, y and y. So that is also not possible here. So we can check for fourth rule. Now see here we have 4 terms. If I take you to that one, we have 4 terms here, but it should be arranged in this manner, y dx, x dy. So let us see that is it possible to arrange it in this form? Let us try. If I consider these terms together, and if I consider this and this together, is it possible to write it in the fourth form? Let us try. Xy square, x square y. Here xy will be common. We will be having y dx, and here we will be left with x dy. Now come to this one, plus x square y cube, x cube y square. So we can take here common x square y square. We will be having 2y dx, and here we will be left with minus x dy equal to 0. Now you can see a is 1, x raised to power a, y raised to power b. A is 1, b is 1, m is 1, n is 1. What is this a, b, m, n? You can check here. M, n, a, b. These are the constant. Again coming to our problem. This is c, this is d, this is p, py dx, and what is q? Q is minus 1, qx dy equal to 0. So in this case, we will be assuming that integrating factor has form. We will be assuming here, assume that the integrating factor has the form x raised to power h, y raised to power k, where h and k are so chosen that when we multiply this equation with this integrating factor, it becomes exact. So We have discussed some cases depending on the rules which we have discussed today. So we will continue the topic, the same topic of differential equations of first order, first degree in our coming lectures. So thank you for now. Namaskar.